All right, let's get right into it. If you work in software engineering, you're probably pretty familiar with traditional database architectures. I mean, for decades, the gold standard for designing a reliable data system was to just use a single leader. You have one primary node, the absolute authority, that dictates the exact order of operations and copies all that data down to its followers. But today we're looking at a totally fascinating system design concept that completely flips that traditional architecture on its head. Welcome to today's Explainer on Distributed Data 21, where we are going to explore the wild, highly available world of leaderless replication and Dynamo. So here is our roadmap for today's Explainer. We'll be hitting 1. Goodbye to single leaders, 2. The magic of quorums, 3. When things go wrong, 4. Fixing stale and broken data, and wrapping up with 5. The availability trade-off.
I want you to really picture your current mental model of a database. In a standard single-leader setup, if that primary node goes down, maybe the server completely crashes or, a network cable gets accidentally unplugged, what actually happens? Boom! Your users are completely blocked from saving their data. Sure, you might have some automated failover process to eventually promote a new leader, but during that window, your application is functionally broken for anyone trying to make a write. And in a global, highly scaled application, literally 30 seconds of downtime can be an absolute disaster.
Goodbye to single leaders. Let's look at a solution Amazon popularized to solve this exact bottleneck, which led to the creation of their famous in-house Dynamo system.
Okay, the crucial point here is that by removing the dictator at the top, we empower every single node to accept incoming data changes. In a leaderless configuration, there is no primary, no master. A client application can just send its write requests directly to several replicas all at once.
This brilliant shift in design gives us what we call high availability, and that means even if a server is rebooting for an update or an entire server rack loses power, your app just keeps humming along smoothly. You don't have to sweat through a stressful failover process anymore. As long as some nodes are still standing, your system is fully open for business.
Section 2. The magic of quorums. Now, getting rid of the leader does introduce a massive new problem. Without a central boss putting writes into a neat, ordered log, how do we make sure data actually gets saved correctly? This visual right here brilliantly illustrates the core mechanism. Notice how the client, user 1243, simply fires off its write request to several nodes at the exact same millisecond. Replica 1 and Replica 2 receive the data and they say, yep, got it. But Replica 3 is totally offline. In a leaderless system, the client completely ignores the fact that Replica 3 is down. As long as a certain minimum number of nodes acknowledge the write, the client just considers it a success and moves on.
But wait, if some nodes miss the write, how do we ever read accurate data again? Well, to guarantee we always read the most up-to-date information, we rely on this really simple arithmetic rule. The number of nodes we write to, that's W, plus the number of nodes we read from, R, must be strictly greater than the total number of nodes, N. This is the whole concept of quorum reads and writes.
And visually, it's so easy to prove why that formula works. Imagine we have 5 replicas in total. If we require 3 nodes to confirm a write, and we also require 3 nodes to answer our read request, those two groups absolutely must overlap. It's mathematically impossible for them not to. As long as our formula holds true, the set of nodes we write to and the set we read from will always share at least one node. And that one overlapping node, it's guaranteed to have the freshest, most up-to-date data.
The best part is you can actually tweak these dials based on your specific application's needs. Say you have a system that does way more reading than writing. You could set your reads to just one node. That makes reads lightning fast. But the catch is, you then have to write to all 5 nodes to maintain that quorum. It's a trade-off. You're basically trading write availability for read speed, while always keeping that essential quorum overlap intact.
Section 3. When things go wrong. Let's move to the real world and see how this creates some unavoidable complications. Because as any back-end engineer knows, distributed system design is literally all about managing trade-offs. Since we're heavily prioritizing availability, meaning we want to keep the system running no matter what, we have to accept a somewhat messy reality. Sometimes network partitions will randomly cut nodes off from each other. Sometimes one node processes requests a bit slower than the others. And sometimes 2 different clients will try to update the exact same record at the exact same time.
This leads us straight into the concept of a stale read. If a node was temporarily offline, obviously it missed some writes. When it comes back online, if you happen to query it before it catches up, it's going to hand you outdated data.
Even with our quorum formula perfectly in place, weird network delays mean edge cases pop up where you momentarily see the past. And that temporary inconsistency, that is simply the cost of doing business with a highly available, leaderless setup.
Section 4. Fixing stale and broken data. So if nodes are just constantly falling out of sync like this, and we don't have a central leader to fix it, how does the database ever actually heal itself?
The first technique is wonderfully clever. It's called read repair, where the client application itself basically acts as the system's janitor. When a client reads from multiple nodes to satisfy its quorum, it might notice, hey, 2 nodes gave me version 7 of this file, but this third node gave me version 6. The client instantly realizes that third node is lagging, and it immediately writes the newer version 7 back to the stale node, totally fixing it for future users.
But wait, what if a piece of data is written and then just sits there? If it's rarely read, read repair would never actually trigger. For that, systems use a continuous background process called anti-entropy. Think of it as the background janitor. It constantly searches for differences between replicas behind the scenes and quietly copies over the missing pieces so that all nodes eventually converge to the exact same state.
Okay, but what happens during a truly massive failure? Let's say a network partition completely cuts you off from the specific nodes that are supposed to hold your data. Instead of just throwing an error and giving up, leaderless systems can use what's called a sloppy quorum. This means the database prioritizes saving the data above literally everything else. It will accept the write on any reachable node in the entire cluster, even if that node wasn't originally designated to store that specific record.
I absolutely love this analogy. Using a sloppy quorum is exactly like being locked out of your house and temporarily leaving a package with your neighbor. The fallback node politely holds on to the data. Then, once the network recovers and the correct home node comes back online, the neighbor hands the data back to where it belongs. This is called a hinted handoff, and it's what makes write availability in these systems incredibly resilient.
Section 5. The availability trade-off. As we bring this all together, we really need to address the elephant in the room. What actually happens when 2 users successfully write conflicting data to different nodes at the exact same time, and there is no leader to decide who is first?
Well, because those writes are concurrent, they don't have a natural order. There is no first. So we just have to force one. A ton of leaderless databases use a strategy called last write wins. They simply look at the timestamps attached to the writes, pick the highest one, and silently drop the older one. Which means, in high-conflict scenarios, even if a system literally told a user their write was successful, that data might just be thrown away later to resolve a conflict.
And this all comes right back to the original motivation behind Dynamo. Think of an online shopping cart. It is far, far better for business to just keep accepting items into a cart and maybe have to sort out a few concurrent duplicates later than to show a customer a frustrating error screen just because a single server's rebooting. You embrace eventual consistency because at the end of the day, availability directly translates to user satisfaction and revenue. So here's the question I want to leave you with today. Leaderless replication requires you to accept a world where data might briefly be stale and where concurrent writes require some messy conflict resolution. But in exchange, you get a system that practically refuses to go down. Does your application truly require strict, perfect consistency, or should you be favoring the unstoppable availability of a leaderless design? Understanding when to embrace one over the other is exactly what separates good system design from great system design. Thanks for joining me on this explainer, and I'll see you next time.